Good evening, class. Today we're going to look at inscribed angles and polygons. This is a little bit different just because we're not going to look at necessarily chords or diameters or tangents or measures of arcs, but they will be part of what we look at here. What we're going to be looking at are what we call inscribed angles. So when I have a circle here, the first thing we're going to learn about is an inscribed angle. So in a circle, an inscribed angle is an angle whose vertex is on the edge of a circle. Basically, the corner of the angle is lying on the edge of the circle. So in the picture that you see there, that very far left point, the one that has the inscribed angle marking toward it, this right here is an inscribed angle. These two rays forming this angle here. Alright, I didn't put a C here, but I should have. Angle ACB is an inscribed angle because the vertex, that corner, is on the edge of the circle. And the sides of it are chords. Okay? That's an inscribed angle. We're also going to be looking at what an intercepted arc is. The intercepted arc is going to be this arc formed by the inscribed angle. So if I look here, this side of this angle, this side of this angle, intersect the circle at A and B. Arc BA is the intercepted arc because it's the part of the circle that's within the angle. Alright? So, an inscribed angle, the corner of the angle is on the circle. The intercepted arc, that's the part of the circle inside the angle. Alright, now here's the neat thing. The measure of the inscribed angle is exactly half the measure of the intercepted arc. Whoa. That's almost seems too good to be true. If I know one, I know the other. If I know the measure of the arc, I know the measure of the angle. Whoa. Wait, if I know the measure of the angle, I know the measure of the arc. And yeah, that's entirely true. If I would look at something here, a circle, and I would draw an angle in it. And I knew it just happenstance that this here is 40 degrees. I would know instantly that the measure of the arc over here, this measure right there, would have to be double that, 80. That's 80, this is 40. And there we go. The measure of the inscribed angle is half the measure of the intercepted arc. Let's use this. Here are 3 example problems of what we're doing. Now it says find the measure of the red arc or angle, but I'm going to let you know after I redraw them which ones those are because it might be a little bit hard for you to tell. Alright, so let's focus on this leftmost picture here. This leftmost picture, they want me to find this angle right there. Well, is angle G an inscribed angle? Well, yeah, it is. Its corner is on the edge of the circle, and it has sides that are chords of the circle. Yeah, one is a diameter, but a diameter is just a special chord. Oh, and the intercepted arc, HI, is 90 degrees. So the arc and the angle have a relationship. The angle is half the arc. So measure of angle G equals half of the arc measure, 90 degrees. So measure of angle G equals 45 degrees. Alright, next problem. I look at it and it says find the measure of arc TV. So I'm looking for this out here. Well, I look. Angle U is an inscribed angle. That is an intercepted arc. They have a relationship. The measure of arc TV is double the measure of the angle, 38 degrees. So the measure of arc TV equals 76 degrees. We're on quite a roll here. We're getting these right and we're ready to go. The last one is the trickiest though. They want me to find the measure of this angle. And look, angle ZXW, arc Z. I don't have the measure of arc ZW. But if I had it, I would know the measure of arc. Sorry, I would know the measure of angle ZXY. Sorry, ZXW. Oh wait, hold on a second. I know the measure of arc ZVW. ZVW. And I know that this here is going to be 2 times the measure of that angle. 2 times 76 degrees. So this measure is actually 152 degrees. Whoa, that's 152 degrees. So measure of our ZW is 152 degrees. So that means the measure of angle ZXW is going to be equal to half of 152 degrees. So the measure of angle ZXW equals 76 degrees. So, for the most part, you're either going to be taking half of the arc, or you're going to be multiplying twice the angle. These are the types of problems you'll see. In fact, the next theorem that we're going to look at is this one right here. Angle B and angle X have to have the same measure, and we know they do if they have the same intercepted arc. That's what the next theorem says. Hey, if two angles have the same intercepted arc, they have to be congruent. Kind of makes sense, because this angle is half that arc, this angle is half that arc, so whatever number this arc has for a measure, both of those would be half of it. So they'd have to be the same. Same thing up here. If I look at arc VX, angle Z, intercepted arc is VX. Angle W, intercepted arc is VX. So whatever the measure of VX is, both angle Z and angle W will be half of it. So angle Z and angle W have to be congruent. That's what the next theorem says. If two inscribed angles of a circle intercept the same arc, then those angles have to be congruent. No way around it. Angle Z and angle W are congruent. Angle V and angle X were congruent. And that's what the picture looks like. So the example here is this one here, which I've gone over in quite detail. So I could have skipped it. Instead of finding this measure of the arc right away, I could have said, hey, angle X has to be 72 degrees because angle V is 72 degrees. All right, concept 13. Inscribed polygons. So now we're not looking at inscribed angles anymore. We're going to actually look at inscribed polygons. And an inscribed polygon has every single one of its vertices on the edge of the shape of another polygon or circle or something of the like. A circumscribed circle is a circle that contains a polygon or shape on the inside. So let's look at what an example of an inscribed polygon would look like. Well, all you have to do is draw an outside shape. It could be a square, it could be a rectangle, it could be a rhombus, but because we're in the circle section, I'm going to just draw a circle. And on the inside of this circle, what I'm going to put is I'm going to put a triangle. I'm going to put a corner here, a corner here, and a corner here. And I'm going to connect them. This would be an inscribed triangle. Why? Because each one of its corners are on the edge of the outside shape. That's an inscribed triangle. The circle on the outside would be circumscribed because it contains a shape on the inside. Circumscribed. And it's a circle, so circumscribed circle. And that's all the idea is here. Now, there are a few things we know about some inscribed polygons. So what we're going to do is, we're now going to look at a few shapes, which, by the way, this is a section that is split into 2 days, I believe. The first part is everything before this. Before we even looked at inscribed polygons. This is now part 2. So, inscribed polygons, the first one we look at is a right triangle. If I put a right triangle in a circle, it's actually going to be in one semicircle, or one half of the circle, or in a semicircle. That's because if I put a right triangle inside a circle, that right triangle will always have the hypotenuse be a diameter of the circle. No matter how I draw it, it's going to be a diameter of a circle. So, let's just look at part 1 there. If I had a group of people, and I knew that my camera had a 90-degree angle lens. And I wanted to know where I could stand so that way I could film this row of people. Where could I have them? Where could I stand to film everyone in the picture if my lens has a 90-degree angle? So what that means is from one side to another side, or what I'm catching in my picture, is a 90-degree angle. Well, draw a circle. This circle is anywhere I choose will form a right angle with that diameter. I choose right here. Draw it to that edge, draw it to that edge up there, and this should be strikingly close to a right angle. Choose another point. Let's choose a point over here. Draw it to this side, draw it to the bottom side, right angle. Whoa. In fact, it does not matter where I choose. Any single spot I choose on this here, on the circle, if I have a diameter and I draw a segment to both endpoints of my diameter, I will always get a right angle form. So a right triangle will always have its diameter be, it will always have its hypotenuse be the diameter, because that's the only way a right triangle can fit in here, is the right angle is over here and it intersects with the diameter. So if you have an inscribed right triangle, you know right away, 100% certainty, that the hypotenuse is the diameter. The other part of this is if I know that one side of an inscribed triangle is the diameter, I automatically know that I have a right triangle. This is actually one way that they sometimes made right triangles in the past, is they would make a line, they draw a circle containing that line, they choose a point on that line and very carefully draw it to both edges, and they would have a right triangle. They would then erase the circle, and then they would find information on that right triangle that they would need to use. But that's how we could construct a right triangle, is by constructing a circle, drawing the diameter, choosing a point on the edge, and that point will form a right triangle with the diameter every single time because of this theorem. Well, let's look at a few ways we might use this. I want you to find the value of each variable. Now, in this inscribed polygon, there's 3 inscribed angles. Use that idea to find each variable. Alright, I realize I didn't put degrees in the symbols. It might not be a bad idea to do that. Well, let's look at this picture. Wait, this is a 90-degree angle. And these chords are of its inscribed angle. So that means that this arc here has to be double the inscribed angle. Well, double the inscribed angle. So that just means y is equal to 2 times 90 degrees, because that's the inscribed angle across from y. So y equals 180. Z. Look, this angle here, angle A, forms arc BC. So arc BC is going to be double that measure. So this is 2 times 30 degrees. So Z is 2 times 30 degrees, or Z is 60 degrees. Sorry, Z is 60 because it's Z degrees. Now there's 2 ways I could do the last one. First, I could find this one and then find the arc. Or, seeing I already have 2 of the 3, all 3 arcs have to add up to be 360. So 60 plus x plus 180 has to equal 360. X plus 240 equals 260. X is equal to 120. And there I go. I found all 3 using the ideal of inscribed angle is half the intercepted arc. Alright, we're going to use a little bit of a different idea. This over here. This arc has 180 degrees, which means arc on this side has to be a semicircle. If that's a semicircle, this is a diameter. If this is a diameter, and this is an inscribed triangle, this has to be a right triangle. So C has to be a right angle. So in other words, C has to equal 90, otherwise that over there won't work, because that has to be a right angle. Wait, if this is a right angle, this arc is 100 degrees, and this arc is formed by angle B here, the inscribed angle B. Well, measure of angle B is going to equal half of that arc, 100 degrees. So this here, measure of angle B equals 50 degrees. And I look, I'm actually asked to find each variable. So I'm only looking for lowercase b, which ends up being 50. If this is 90 and that's 50, all three angles of a triangle add up to be 180. So 90 plus 50 plus A equals 180. 140 plus A equals 180. A equals 40. So, if you ever want to construct a right triangle inside of a circle, use the diameter. The angle across from the diameter is the right angle. That's it for this concept. We're going to move away from triangles at this point, and we're going to look at quadrilaterals. Now, we've looked at special quadrilaterals already. We've looked at rhombuses, rectangles, parallelograms, so on and so forth. Not every single shape can be constructed inside of a circle. Yeah, not every single shape can be constructed inside of a circle. In fact, there's only certain quadrilaterals that can be, and these are the quadrilaterals that can be. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. Whoa, whoa, whoa. Why do opposite angles have to be supplementary? That seems kind of extreme. In fact, that kind of eliminates a few. In fact, besides isosceles trapezoids, I think that completely eliminates trapezoids. It also has a chance to eliminate kites. So there's a little bit of an issue there. So, let's draw a circle, and let's put a random quadrilateral in it. One side here, one side here, one side here, and one side here. Now look, that's not even a parallelogram, that's not a trapezoid, that's not a kite, that's not a rhombus, it's none of those things. But it's the only type of quadrilateral that can be put in here, because its opposite angles are supplementary. How do I know they're supplementary? Because this arc here, in green, is associated with this angle. And this arc here, in blue, is associated with this angle. I'm going to make a different mark here. Wait. This arc and this arc combine for these two angles. Those two arcs combined is 360. What's half of 360? 180. So these two angles together always have to be 180 degrees. Because between those two angles, their intercepted arcs account for the whole circle, 360 degrees. And those two angles are half of their arcs. So if they add together to be 360, when they add together, if the arcs add together to be 360, the angles add together to be half of that, 180. So the only types of quadrilaterals that can be thrown into a circle or inscribed into a circle are ones that have angles being supplementary. Opposite angles being supplementary. Alright, so let's look at this. Find the value of each variable. Alright, so I look at this. Both of these shapes are quadrilaterals. So wait, the last theorem just said that the only type of quadrilateral I can put in here are ones that have opposite angles being supplementary. So I look, the only way this quadrilateral is inscribed is if this angle here and this angle here, opposite angles, add up to be 180. So 100 plus 4x has to equal 180. Consequently, this opposite angle, 5y and 85, also have to add up to be 180. So 5y plus 85 has to equal 180. This is the only way that shape is inside that circle. So let's solve for x and y. Subtract 100 from both sides, 4x becomes 80, divide both sides by 4, x is 20. That's the only way this shape is inscribed. Solve for y. Subtract 85 from both sides, 5y equals 95. Get y by itself, divide both sides by 5, you get 19. The only way this works is if y is 19 and x is 20. That's the only way that is inscribed. The one on the right is slightly more challenging. Either way, I have to first of all find what j is. Wait, this is 80, this is 80, this is 90. All the arcs measures have to add up to be 360. So if I would do 80 plus 90 plus j, that has to equal 360. So 250 plus j has to equal 360. So j is truly 110. So I found my first variable, j. 110. Now I'm looking for the measure, or I'm looking for m and k. Well, this angle right here, its intercepted arc is not just 90, and it's not just 110, it's the full length from this point here to this point over here. So it's 200. But 2k isn't 200, it's half the arc. So 2k equals half of 90 plus 110. 2k equals 100. K is 50. Repeat it for m. For m, this corner and this corner right here are what help form this angle here. So the arc I'm looking at for 3m is not just 110, it's not just 80, it's the combination of the two. So 3m isn't equal to 80 and 110, but it's equal to half of that. So 3m equals half of 190, 3m equals 95, and m here equals 31.6 repeating. Can't believe I made a decimal there, but that's what I got. And there you go. That's what you would have to do here to find these measures. Okay, so the only way a quadrilateral is in here is if its opposite angles are supplementary. Another thing to note, you can also still use the inscribed angles and their intercepted arcs to find measures that you're looking for. And that's what we had to do here. Alright, the last thing we're going to look at for this section is this. What shapes can always be inscribed in a circle? Explain. Can a rectangle always be inscribed? Yeah, all of its angles are right angles. So rectangles' opposite angles are automatically supplementary. 90 plus 90 is 180. How about a triangle? In number 2, can that always be inscribed? Yeah, it always can. The diameter will be the hypotenuse. How about an isosceles triangle? Yep. In fact, if you remember back to, I believe it's chapter 4. No, it might be chapter 5. But there's something called the circumcenter. And that's the center of the circle that we could draw a circle that inscribes the triangle, or it's a circumscribed circle. Wait a second. So there's a center of a triangle that can always have a circle be drawn such that the triangle is inscribed. Yeah, there is. So 2, 3, and 4, yeah. Each of those triangles have a circumcenter somewhere. So they have to have a circumscribed circle. Possible. So always. The first 4 are always. 5, sometimes, if the parallelogram is a rectangle or a square. A kite, sometimes. No. That one's a never. I take that back. There is a possibility for a kite sometimes. I'll let you figure out on how that is done. A trapezoid, only if it's isosceles. 8, yeah, it's always. Alright, that's what you're going to have to do for this section here. If you have questions on some of the last ones, it's not going to take too long. If it's four-sided, opposite angles have to be supplementary. For the last 4, the only one that could happen for is the kite and isosceles trapezoid. Isosceles trapezoid is always, a kite is sometimes. Parallelogram is also sometimes. So the last 4 are sometimes. But anyway, those are the 4 ideas here. Inscribed angles, half measured arc. Shapes can be inscribed inside of a circle. A right triangle has the diameter being the hypotenuse, or the hypotenuse being the diameter, either way you want to say it. An inscribed quadrilateral has to have opposite angles being supplementary. Well, that's all for this section. Till next time.